That sounds like we're ready to go. Okay, so you guys voted. I'm Bob Harper. I'm here to lecture this year about really basics, fundamentals of programming language theory. The last few years I've been doing crazy high-dimensional type theory that I've lectured on here. This year I decided to go back to fundamentals. So this is what I'll be speaking about in the next few days. I'm sorry that I wasn't here on Monday. I was in Oslo last week and I've been in transit and I'm all jet-lagged all over the place. So here's what I'm going to do. I'm going to give a series of lectures and I'm going to pick out some topics that I think are illustrative of some fundamental ideas, and I'll use them. I'm going to have to rely on you. What I'm really trying to do is teach my whole undergrad PL class in 4 lectures or 5 or something, and obviously I'm not going to succeed in doing that. So some of you know these things, that's fine, and maybe I can help amplify and clarify certain points. Others of you may not know them. This will give you a flavor, and I'll mention that the backing store for my lectures is the PFPL, Practical Foundations for Programming Languages, and recently I've written about a dozen supplementary notes, which are also there. I hope you can read the board there. I have a tendency to write too small when I'm up close to the board. You can have a look there. And I'm going to put on these essentials, I'm going to put on the side here stuff that I think you should have for background reading that I don't have time to lecture on. If I start lecture on these things, I'll get absolutely nowhere interesting. So I'm kind of going to skate a little bit, and I'm going to rely on you to fill in the background. There's study sessions, I think, later today. Is that correct? Is that correct? There's a study session at 4 or something like that? Usually or we have lectures booked up. I didn't do the scheduling. There are lectures all the way. Okay, well, we'll figure this out. I'm happy to come for a study session, let's put it that way, separately from my lecture to back up my lectures and give you some clarification. And I understand from mail that I got from Jim, I think that there's some note takers who are taking notes, so that would be great. I hope they'll be helpful for you. Thank you. I don't know, maybe it's you guys in the front. I don't know who's doing it, but whoever is doing it, thank you for doing that. I think that'll help everyone. And then things are being recorded like they usually are, so I have to be careful not to curse too much. So I'll try not to do that. Okay, so this is where we'll start out. And so what I'm motivated by, at least for today's lecture especially, is Robin Milner crystallized a question a number of years ago, it was really quite some time ago, that I find rather charming to ask, which is the question of what does it mean for a programming language to exist? Well, it's a perfect question because it simultaneously sounds like a stupid question, and actually then you realize maybe you're not so sure how to answer that. Because the typical thing, obviously, is some product comes down the pike from some company doing some random 1970 thing and making all the same mistakes all over again, and then, that's what it means to exist. You download version 3.6.1, and that's the thing, okay? And that's the way it is. But I think, as it becomes more important for people to understand and actually prove rigorously properties of languages and properties of programs, that state of affairs is not satisfactory. And yet, in full-scale programming language that it can be properly I'm going to describe here. Everything else that I know me is just a pile of crap. It's just sort of like, oh, whatever, and then they discover years later, people spend a chunk of their life trying to prove that some language I won't name actually makes sense. They say, oh, well, whatever, okay? So it's like a crazy state of affairs. So, yes, I hope I can hear you.
Which language do you think exists then?
Standard ML is the only one that I know of that has a that has a proper definition, okay? So the question I want to say here is I want it to be a mathematical entity, a mathematical object, subject to rigorous analysis. Okay, a hunk of code that you downloaded from some GitHub doesn't qualify. Okay, not at all. Okay, so that's what I'm looking for. And so the methodology that has emerged over years, and many of you probably already know it at least to some degree, is what we tell students in class, but it's not practiced. And why? That's a mystery to me. I recently had a conversation with someone who's a researcher in the area, and he told me that they were doing a well-known programming languages, and what programming language they're going to revamp and revise and so on. And I said, oh, good, are you going to have a definition? And that person's answer was, no, we decided that it's already been done. And I like incredulous because I thought, oh, that means you're not even going to tell us the grammar for the syntax because, Algol did that in 1960. The hell with it, right? Why should we even tell you what the syntax is? It's completely crazy. So we have to have a notion of, we'll just say the abstract syntax. That is, what are the things that we're talking about? What are the entities? What are the programs? And so on. I'll say abstract because I don't wish to enter into the very difficult question of concrete syntax, which I consider to be overlapping with issues of psychology, to be honest. And yeah, really. And it would be interesting to do something rigorous and serious about that, but as far as I know, no one's ever done it. And the same applies to error messages. It's another psychological issue. Okay, and so I don't know, but I don't have anything to say about that, so therefore I'll ignore it. Okay, the other thing is what I usually call the statics, which is the formation, what it means to be a well-formed program, and the dynamics, which is how to run it. Okay, which is execution. And my point is this: running code is the ground truth. Okay, so this establishes us the truth about what is going on. Everything else is kind of parasitic on that, and I'll explain what I mean by that in a minute, what is going on. I should finish my sentence. Okay, so everything else is parasitic on that. Okay, so there's a certain kind of back pressure that comes from what the dynamics is going to be to tell us what the static should be, which tells us like how we should formulate the syntax, which tells us what it means for the programming language to exist. And the criterion that we want, the answer to Robin's question is, these should be coherent. And the idea, as the terminology suggests, the dynamics is about what's really going on when you run things. The statics is some approximation to the truth given by some formalism. The formalism, by virtue of being recursively enumerable, can never come anywhere near the truth. It's not any remotely close to the truth. Okay? That's the thing to keep in mind. That's Gödel's theorem. Okay? And so what we want to do is we have useful ways of predict, but the point remains that the statics is a prediction about the execution behavior. And this is the thing that we'll be interested in understanding about the coherence. I want to make accurate predictions. So if I tell you that something is going to compute a string, it bloody well ought to. Okay? That's the whole idea. Very well-known programming languages do not have this property. In fact, almost none of them do. So I'm asking for more than is typically delivered. Okay, so that's the premise. Okay, so that's what we're going to look at. So I'm going to start out, I came up with some new way of thinking, a new example that I'll start out with. So the starting point that I'm going to do, new to me, I mean new, like I haven't taught this way before, I'll try it out. So I'm going to start with circuits, which are basically forms of Boolean expression. And what I'm going to do here is I'm just going to build up the basics of basic forms of circuits and then look at the passage to the digital domain, the fact of a full-throated computability, a language with full-throated computation, I will model in this setting. I have a number. What I'm going to do is I'm using this as an excuse to bring up a whole bunch of topics. Okay, so that's what's going on here. Okay, so good. So this is a Boolean expression. So this is what I'll start out with. I've forgotten what I actually did. I kind of know. I was just looking at this in the, I'll double check. Right, okay. So I'm going to have the following. It's going to be very elementary at the start. I'll use a typical BNF syntax. If you study over here, you can see what it all means by looking on that topic. So I'll do usual BNF syntax, and then I'm going to do something that's slightly strange here. I'm going to have two forms of let me write it down here. I could have some more, but as it turns out, for the purpose of my lecture, at the moment, there's going to be one more thing I'm going to need, okay? But I'll wait to get to that. So this is my weird syntax. That's a NOR, okay? And I'm going to have two different NORs, okay? And it's important, okay? So that's the first point I want to make here. So you probably know where I'm going. So the picture you see in the textbook looks like that. Okay, and we have two inputs. So let's see here, I call them E1 and E2. So that would be like that, and this would be the output. Okay, so that's a typical textbook picture. But your typical textbook picture, in fact, I think in my notes, which I might give you, I wrote them in Roman numerals, don't ask me why. there's really kind of two sorts of NOR gates you need, and I'll show you why. You don't really, one is a reflection, but I'll show you what it means, what I'm doing, why I'm doing that. That'll come up in a minute. Okay, so now I have a choice. I can either tell you how to execute things or I can tell you what the statics is. I don't know, there's a choice. So what does the statics amount to? I have to go back and forth with this. So the statics is pretty straightforward. It says, when is a circuit well formed? And I'm being provocative here because I know you're going to ask me some question, okay? Oh, in fact, I'm gonna need 2 additional constructs here. I forgot what I had straight away. And as a matter of fact, maybe I'll just start out like this. Let me put it in, I'll change it here. It's a little undermotivated, but I'll put in the notion of a variable. So the first part of my lecture is about the notion of a variable, which I want you to understand accurately. And I feel that it's not completely so well understood, possibly. I don't know. But anyway, I'm gonna talk about that. Okay, so when is a circuit well formed? Well, the critical idea, and this some of you will have seen before, is I have to decide. Okay, so at the moment, what I have is the following thing. I'm going to have, first of all, the notion of E as a circuit. Or if you want to write it, I could write it like that. It's a judgment that says E is a well-formed circuit. Or I could use other syntax. I could say that that's a Boolean. I could say that that's a level. I don't know what to. I couldn't figure out, actually, which was the right word to use. So we'll just be loose about it. So we can say E is a circuit. So this is the idea, is that E is a circuit. Okay, so that's a standard thing. And think of it as computing a Boolean. That's what I'm doing here. These are my 2 Booleans. Okay, so good. So that's what we're going to do. And I could define this if I hadn't bothered about the variable. I can just define this straight out. And you're going to be a little annoyed, I think. And I want you to be a little annoyed because I'm being provocative. Okay, I want to provoke something in you. Okay, so I can write out something like this. True as a circuit, false as a circuit. You're going to know what I'm going to write. Okay, you could do it in your sleep. And why? Because I gave you the grammar, and you're going to say, well, what else do I need to know? And I'll just put star here because there's 2 rules, one for each form. I won't care. So NOR E1, E2, and that's going to be also a circuit. And then I would be done. Okay? And you would wonder, with great full justification, why I even bother to do this, because I've already said it. Modulo this particular thing, I've already said it. Well, that's true. Okay? Until I tell you the following thing. Now I introduce the idea of a variable. And then the critical thing is that every programming language has something called a variable, and only in about 10% of them is it actually a variable. Okay? And that's a terrible fact of history, because going back to the 1950s, it was totally kick-ass to be able to have a memory location named X and be able to write the expression X plus Y, which really meant fetch the contents of X, fetch the contents of Y, and add them. It does not mean what it meant in school. So this ruined computer science and programming languages for a hell of a long time. Because, yeah, in the 1950s, it was amazing. Who the hell wants to write, load X into R1 and then load Y into R2 and then add, R1 and R2 to R or something like this? Who wants to write that? That's terrible. This was a lot better. I used to do this when I was a kid, but not anymore. I used to do assembly machine language programming in the lights on the front panel of a computer. Now I do higher dimensional type theory. It's a little bit crazy, okay? But it all makes sense because, I'll go back. Okay, so here's the idea. So you might wonder, why are we doing this? And the reason is I have to have the notion. And the notion is what you learn in elementary school, which is that it's a placeholder. And it's not a thing. I don't know what else to say there when I say it's not a thing. There's no such thing as a variable. It's a placeholder. And so the point is, the reason we want to do this is that we want to say that, so what does it mean in this case? Not a thing. It stands for a circuit, in this case, to be determined. Okay, that's what we do. That's the important point. That's what you learned in school. And undoubtedly you loved that because you wouldn't be sitting here if you didn't. Okay, so this is one of the greatest achievements of the human mind, and it's so fundamental that you can hardly even think of it being invented. But it actually was introduced by the great Muslim and Hindu mathematicians Al-Khwarizmi and Brahmagupta. It was historically traceable to specific people introducing the idea of variable. I think it's not known who influenced who there. Okay, could be one of them was copying. Okay, but it came about the same time. Okay, so it stands for structure B. So you know about this. So how do we do this? We express it through the notion of a consequence relation, which goes by other names, entailment, and so on. And what are we doing? We're specifying the meaning of variables. And in a PL context, unlike a math context, it's a somewhat up for grabs. And that's a source for confusion because there are different things that variables can be taken to mean. Even once you're in the 10% that actually have a notion of variable, which is a proper notion of variable, it's still not pinned down, okay? Because programming is different from mathematics. There's a lot of influence from math, that's for sure. We like to pretend or think that we'll influence back. I think that's been successful to some degree. But in any case, they're not the identical subject. Programming language is not logic. I'm going to get to this in a minute, but logic is influential on programming languages. So I'll show you in a minute about that. Okay, so specifying the meaning of variables. So that's the idea. And now you've seen the kind of syntax. What I do is I'll just number my variable x1 through xn. And I write that it entails that E is a circuit. So this means E is a circuit, assuming, and now everything is on this idea of what assumption means, assuming that x1 through xn are circuits. So in school, when you finally got to multivariate polynomials or something, you would be writing, x1 squared plus x2 squared is a polynomial. You didn't use this notation, but that's what you were doing. And as you may know, especially when you get to calculus, it starts to get very murky what all these things mean. It's sort of not so clear at the elementary level what the binding and scope principles are. That's the thing I want to come up with. Okay, now a thing that you need to know if you don't know about it is the proper idea of what is an inductive definition. Okay, as I said, this is one of these things I'm going to skate over. I'm going to glide here, and I'm going to skate right over it. And what I'm going to say, so I forgot to add one additional rule, which I'll put here. So if I have x1 through xn, if x1 is a circuit through xn is a circuit, then some E is a circuit. Then some xi is a circuit for any I you pick between 1 and n. Okay, so now I've written a set of rules. I'm going to claim that constitute a definition of the statics. What does it mean for me to claim that it constitutes the definition of the statics? Well, all these rules do is they tell you, well, if these two things are the case, then that is. It doesn't tell you what isn't the case unless you specify it's the least thing of this kind. That's an inductive definition. Okay? So this is a kind of universal or least, I can say least relation such that closed under rules. That's a shorthand, closed under some rules. It is widely misunderstood, it seems to me, just by observation, empirical observation, that people don't even understand that. They write all sorts of rubbish on top of rules and just follow some pattern. I don't even know why. Okay, kind of think it's an implication. It's not an implication. In particular, the closure condition can never hold vacuously. It doesn't make any sense. Okay, these are not implications. They have the flavor of, if these things are derivable and those other things are derivable, that will follow out. Okay, but it's going to be inductively defined. I'm not going to have further time now to say anything beyond this. In fact, I frequently will write this rule in what I call local form. I will just write the following thing instead. I did that deliberately just to show you, but what I wanted to say is this. I can say, if you assume X is a circuit, then X is a circuit. That's the rule I really want to write, and that is what I will call local form. It seems kind of obvious. If I'm assuming it's a circuit, then it is. I mean, because that's what I'm assuming. Okay, so that's what I do. Now, the thing you have to understand is when you make an inductive definition like that, there are various ways to think of how does the inductive definition work. A common one is to make explicit the context everywhere. I won't write it down on the board. By putting it typically capital gamma, and you put in capital gammas everywhere. And except here, you sort of put one more on. And that's like the way people interpret it. That's the sort of defining the total space. There's a certain way of doing inductive addition that way. The way I'm describing it here is what's called the fibered method. I'm using it as a family of things. It doesn't matter. So what it means here is that implicitly, you can write gamma turns. That's all. I'm going to leave that out. It's a virtue of the kind of language I'm considering here that I can do that. So this would implicitly have a gamma here. But I'm not going to do that, okay? But at the end, it's going to define this so-called hypothetical judgment. Okay, so the one way or the other, you have to do it. So in the book and other places, in the supplements, you can find an account of that. Okay, so that's the first thing. So what does it mean to be inductively defined? It means it has a mapping out property. It means that I can reason from the fact that something is derivable by considering all the cases doing rule induction. That's the definition of it. So that's what we're going to do. Now, what do we say about the dynamics? I'm starting out deliberately being ultra trivial because I want to motivate some moves that are some common moves, and I want to show you why they come up. Okay, so the first thing, I could do this first, I don't know, or I can tell you how to execute things. So this is how to execute. How to evaluate. In this case, you could use the word evaluate, whatever you want to use. Okay, we do it like that. And I'll start it out like this. E evaluates to B. I'm starting it like this because, there's some method to my madness, so you'll see. So I'll start out like this, we'll do that. Okay, so E evaluates to V. How do we define this? It's typically also inductively defined. Okay, in other words, I'm going to give you a bunch of rules. So what I need is the following thing. True evaluates to itself. False evaluates to itself. Okay, then, and now the important thing. If E1 evaluates to false, then E1 nor, in the sense sub 1, let me write Roman numeral. That's why now I remember why I wrote Roman numeral. I didn't want to confuse it with this. Okay, this is going to evaluate to true. Is that what I want to say? This evaluates to true, then this evaluates to false. That's what I want to say. I was doing Dan for a moment. Okay, you'll get me right here. It's important that I said this, okay? Why? Because the other form works like this. If E2 is high, then the whole circuit, the whole output is false without regard to what's in E1, or the same thing here. It's necessary to have this. If you don't have something like this, whether it's achieved electrically or achieved by an inductive definition, you have to achieve this. You must do this to make the thing work. Okay, so here's what we do. Then the other thing is that if this evaluates to false, okay, then I want to know, I have to look at what this guy is. So now there's different notational conventions. I'll use this one. Let's do this. Okay, then what is the NOR? I'm reversing this. Okay, and I hope I did it right. At the blackboard, I'm known to make like really stupid mistakes, so I hope you'll fix it. And then besides at the blackboard also, but definitely at the blackboard. Okay, so these are, I think this should come out to be true. So I'm negating E2 in that case. And then I'll just write similarly for this sub 2. Okay, good. That's what I'll do here. Okay, so I'll say that constitutes, I hope I'm right, yeah, that constitutes an inductive definition. Notice, this is supposed to be closed. And this is going to be closed. What do I mean by closed? No free variables. Okay? That's the point. I'm just evaluating things where I know everything. You can't evaluate. You could have a logic for reasoning about equality of circuits. That's what people do in hardware verification, low-level hardware verification. That takes account of the variables and stuff. That's a logic for equality for them. But for running it, I only care about things where all the wires are plugged in. If you have an open lead, it doesn't do anything. Okay? All right, that's the important thing. That's why it's a circuit. Okay, we'll get back to that in a second. Okay, so this is my definition, okay? Now the question you have to ask yourself is, why did I define anything at all? In some sense, why is this a programming language? The reason is, it's very elementary here. So the fact here is this. If E is a circuit, meaning it has no free variables, so if I want to be emphatic, I could write something along the lines of empty turnstile circ. Okay, that is, it has no free variables. Then, in fact, there exists a V, which is either true or false, such that E evaluates to V. Or I could say E evaluates to either true or false, however you would like to write that, okay? And it's a simple proof by induction on typing, on the statics. Why? It's a mapping out property. If something holds with respect to the statics, then something or other else is true. I'm mapping out. So the only thing I can do is just an if-then. There's like no options. Okay, so the only thing I can do is induction on the statics, and then it's trivial to push this through. Unless I screwed up, but I hope I didn't screw up. Okay? So all I'm doing right here is coverage checking. I'm making sure that you covered all the cases. Nothing subtle comes up until a few minutes from now. Okay, but this is the point that I want to make. So we can prove that, and I can claim now at this point, I have a well-defined programming language according to the criteria I'm wishing to illustrate. Okay, so that's second thing. So that's inductive definitions, and in particular, I'll write of statics. Did I make a mistake? What?
Do you mind writing a bit bigger? It's hard to see in the back.
Try to be here.
Larger font.
I'll try. It's hard to do. Okay. Thanks. Of statics and of dynamics. Okay, so that's a kind of background to what I'm doing, so I'm explaining this here. Okay, so that's my definition, and I claim that's good. So using this, I can draw diagrams that look like this. Many of you will know where I'm going. I can draw diagrams that look like this. I can draw two such diagrams, and for reasons that you can anticipate, I'm going to write it like that. Okay, 1 and 2. And then what I wish to do with this thing is I want this to be the input to that. It's still just a circuit that I can write out. And now what I really need to do to pass the digital domain is I need to figure out how to make this go into that simultaneously. I have to have them both. This is invariably called X, that's invariably called Y. This will be the output of interest. The picture describes what is called an RS latch. Okay, so that's what we're doing here. So the question is, how do we deal with that? What does that ... business mean? Okay, so this is where I'm heading. So the point is that if I don't have this in here, you can write that down as an expression in the language I've written. Okay, you take these as input, call this thing X prime just temporarily, just because you want to do it. Call that Y, so this will be Y because it's sort of the same wire, you could say. And then I have an expression. This is perfectly fine in the current language. So this is okay now. That is, that thing above is a circuit. Okay, so that's the important thing. Okay, next thing I want to mention, which I think will be, doesn't really come up for a minute. So let me think for a moment how I want to do this. Okay, I'll mention it right now. You'll notice here that this thing is just saying I can conclude what I assume. So this is sometimes called the hypothesis or reflexivity rule. So I want to just review with you something or what are called the structural properties of entailment. And here I need, and what am I doing when I say this? I'm characterizing, what am I doing? Why am I doing this? Okay, I'm characterizing the behavior of variables. That's what's happening. So the first one is called the reflexivity, is what I said before. In the case of circuits, it just says if X is a circuit, then it's a circuit. So I'm repeating this. But what I'm going to say is these are true facts, so these are said to be admissible. Okay? So what does it mean? I want them to be admissible means that this is something you can derive according to these rules, which you can because it's one of the rules. So this one is trivially admissible. Well, there will be some others. One is called substitution or transitivity, which this is where we're really talking about the semantics of variables. And I'll say the following thing. If E1 is a circuit, and assuming X is a circuit, E2 is, then the whole idea of plugging in is exactly just substitution. So then we'll say that the substitution of E1 for X, E2 is a circuit. I have 3 other things I want to say, but let me pause for a moment. So make sure we see this. So what I mean by substitution is covered here. Right now it's extremely elementary. You just plug them in. It's the most easy thing in the world, like you did in school, okay? But it can get a little bit more complicated, and it's really easy to get it wrong. Okay, so this is just the plugging in property that we expect to have. I can discharge this assumption by providing another circuit to plug in. So in particular, with my inconveniently obscured board, I could think of this as arising by taking that, yes, one moment. I can think of this as arising by taking that circuit and plugging it in for Y here on this circuit. Yes, yes.
What do the R and T stand for on the left? On the board?
Reflexivity and transitivity. Thanks for asking. Yeah, or AKA substitution. So you could also call this substitution. Okay, these things you have to have, otherwise you don't have a notion of entailment. If your programming language doesn't have this property, then something is wrong. In particular, maybe your things that you think are variables are not variables. And that happens, okay? Definitely happens. So I'm telling you, these are school variables, grade school variables, okay? They behave properly. Now there's some other things we can also ask, okay? We can say the following thing. It's a little weird. Any univariate polynomial is automatically a multivariate polynomial, okay? That's called weakening. So it says, well, one way to write it is, if E is a circuit, in other words, we have some ambient context that I'm suppressing here, then with respect to any variable I feel like that's not already there, so I'll say it's not in E, I'll write it like that, then E is still a circuit. And what I mean here is I'm suppressing an ambient context. Okay? So in other words, if I write a multivariate polynomial in Y, a univariate polynomial in Y, I can think of it as a multivariate polynomial in X and Y because I just happen to not use X. Okay? So that's called weakening. So this you take for granted. And my whole point is, these you cannot take for, like, these are totally essential. These are somewhat defeasible. Substructural logics have less than these properties, and I'm not going to get into that at all. Okay? So I'll just deal with this here. Okay, the second thing, which is a little, let's see. Oh, yeah. This one is always annoying. I don't know what to do about it, but I'll just say this. If X is a circuit and Y is a circuit, and you get something that E is a circuit, that's the same thing as if you write the assumptions in the other order. It almost seems to go without saying, but in actual fact, when you deal with substructural logics, that may not even be the case. And that's called exchange or swapping. Exchange. So the X looks like what you're doing, okay? So that's what we do there. And then the other one is what is called contraction or shrinking, okay? And the idea is that, assuming X is a circuit, I can, this the other way around. So I want to say if X is a circuit and Y is a circuit, tells me that E is, then I'll write it like this. I'll use a different variable, but sometimes it's formulated in other ways. I'm allowed to plug in the same variable for 2. And that's going to be a circuit. This is called contraction, which contraction, you could also call it proliferation, maybe. I don't know. I'm allowed to use 2 things for 1. One thing for 2, excuse me. Plugging both of these in the same thing. So in other words, it says I can use a circuit more than once. A circuit more than once. Okay, that's it. Now the claim is, what I'm really saying here is, the following are admissible. Okay, that's the claim. That is, the idea of admissibility. And what does it mean to be admissible? It means, if according to the statics, I'm doing a reasoning by induction, if this premise is derivable according to the rules, then so is this. So what do? I go by each of the rules which are up on the board right here, conveniently, and I check that if I throw in some extra variable, everything is preserved. It's fine. Nobody cares. Why? Because right here, I said implicitly this is universal in gamma. It's natural in gamma. a certain implicit the fact that there's a surrounding context. So of course, if there's a surrounding context, I want to add in y, I'll just assimilate y to the surrounding context and derive what I need when I'm done. Okay, it's very easy. So that's what we do there. Okay, so you can prove each one of these things by an induction on the statics that we've given here. You can do the same thing here, and you can do the same thing here. Okay, so that's an important setup for what we want. We're going to need that. Okay, this will come on. But what I'm doing is telling you I'm telling you that the behavior of variables. I'm telling you what variables mean. They stand for any circuit. Okay, and now the important thing is this. Why is it important that these are admissible? What it does is it expresses limiting conditions on what you can do in your programming language. On the language. In particular, and now I will bring up another thing, okay, which will come in here. They're limiting. The important thing is these conditions are limiting. There's a tendency in programming language design, I'll say it like this, to throw in shit for convenience. Okay? Oh, this is my favorite example. Look, this thing looks so cool. We'll just throw in this thing. That'll be great. Python, as an example, is a big pile of conveniences, supposedly. Okay? What I will say to you is this, a lesson that I hope will take away by the time I'm done. The expressive power of a programming language arises from its strictures and not from its affordances. Memorize that statement. It's really important because if you make restrictions, you can relax them in a selective manner. If you don't make restrictions, you're screwed. Once everything is one big bucket, that's it. There's your slop bucket. That's all you have. If instead you carefully partition things, you can decide to coalesce them. It's like a quotienting. If I make distinctions, I can relax them. If I fail to make distinctions, I've shot myself in the foot. Listen to me, okay? That's a really important thing. So these are limitations. I'm going to show you a very important mistake, I would say, that violates this principle coming up in a minute. Okay, so they're expressing limiting conditions, which your instinct is to say, oh God, the last thing I want are limitations. Now, you're young enough, you won't appreciate this point, but there was a day when, probably is even still true in some circles, the very idea of having type restrictions is considered, a severe imposition that cannot be tolerated. Or the very idea of doing math constructively can be regarded or is regarded as a severe imposition that cannot be tolerated. No. Because you see, if I make type restrictions, I can decide to identify all the types and say, oh, what you're talking about is you only have one type. I'll amplify that in a minute. As opposed to you have no types at all. A very important distinction. Another thing which I can't amplify here, classical logic is a special case of constructive logic. I decide to obliterate a distinction that I would otherwise make. Good, I can do that in a controlled manner. It's great. Okay? I'm not lecturing on that topic this year, so I won't go any further with that. It's the restrictions that matter. Okay? So I know it's a little counterintuitive, but I think it's very important. Okay, so that's what we have there. So that's good. Inductive definition is good. All right, so now the next thing I want to do, which just sets me up this. Oh, yeah, so the next thing I want to do, but before I do it, okay, I did that. Good, did that. Good. Okay, good. Let me raise one other issue, one other point. So this will be like an exercise, really, almost, which is an alternative formulation. That uses what are called BDDs, which are called binary decision diagrams. Which are used a lot in hardware verification. What are binary decision diagrams? Conditional expressions. Okay, so the point is what you do is you change your syntax and you look like this. I have variables, I have true, I have false. But instead of these weird ad hoceries about these nors, I just have an if, E1, and E2. And that's called a BDD because what you're doing is you're taking the E and you're branching on whether it's true or false. And then you have a circuit here and you have a circuit here. An important issue is that these can be shared structure. I'll put it out like that. That has to do with the engineering of it. Let's not worry about that right now. Okay? So the important point is it's a conditional expression. Then the exercise is just to set this all up. And then you can define, for example, this nor to be, by definition, just standing for, you look at E1. If it's true, then your answer is false. And if it's not, your answer is, all right, not E2, and then you can define not. Guess what you do with it? You do a Boolean test on it and go false and true. Okay, now I'll note, then this allows me to make another remark. So you can do this. It's very obvious to you, I'm sure, but I'll just mention it. So the point is, in a certain sense, I can say if E1 is equal to true, I'm testing whether this is true, and I'm testing whether it's true or whether it's false, and I consider that to be sufficient. You can, again, prove the termination theorem using these diagrams. You should check for yourself that you know how to do that. It's important. That's where evaluates to either true or false comes in, because you need to know I've covered all the cases. How do you know there's not a third Boolean? In very popular functional programming languages, there is a third Boolean. You can't get rid of it. Do you know that? Do you realize that? Okay, you have full-scale programming languages that cannot express bits. What? Okay, I'll come back to that later. Okay, so you can write it out like that, okay? My point is this. The reason I want to bring that up is you could ask yourself, what is the difference? If you look at the syntax, just look at the syntax. I didn't put you through all this suffering. You just look at the syntax. Can you tell me what's the difference between X and true and false? They're all the same thing. There's some atomic thing. And yet, whereas it does make sense to ask whether something is equal to true or something is equal to false, you can make sense of that with the conditional. It does not make sense to have a programming language concept which checks whether one variable is different from another. Why does that not make sense? Because it's not stable under substitution. Why? Because I have contraction. And if I have contraction, I can plug in one variable for two. So over here, X is not equal to Y. But then that would mean Z is not equal to Z. Nope, you screwed it up. That's why you can't do it. That's why variables are not the same as constants. That's why I need more than just a grammar. Okay? So I'm giving you all the inside baseball. That's what I'm trying to show you here about how these things go. That's why we do these things, okay? There's a reason for everything. So I'm trying to show like all the inner game of what's going on here. Okay, so good. So I finished with that. That's what I want to do. All right, now let's go back to the question I asked a few minutes ago. I don't know where it is. Oh, yeah. How to set that guy up. All right, let me think about my board space. Something has to be erased, so I'll erase here. Hi, okay, we're back. All right, so I needlessly confused a bunch of people, I realized. I meant for this simultaneous substitution. Plug in Z for X and also Z for Y. It's an instance of a more general thing of simultaneously plug E1 for X1, E2 for X2, however many you want in E. That's an instance of that. So that's what I meant. It's just the idea that I showed at the board someone, if you think of this as a circuit, I'm allowed to do this without worrying about anything about attenuation of signal strength or anything. I can just plug in X, I can run that wire and I can split it and send it to both X and Y, and I don't have to worry about any physical effects. Okay, I'm just allowed to write that. Okay, so that's what's going on here. Okay, that's the point. Okay. Okay, so good, I got to that. So now what I want to do is someone asked me the question, oh, how the hell are you ever going to write this down? Like, why did you remove that dotted line? It seems like you're cheating. And well, yeah, that's kind of true in a way. Okay, so let's write out what I'm doing here. So a way of writing this is I can say X is by definition, what do I call it here? R nor in the sense of 1 to Y. And I can define Y to be X in the sense of 2 with S. Okay, this is a way of writing those pictures that's a little bit more concise. Now, if I want, and I am going to want this because I indicated that X is the output of interest. So I can write this instead. I can say, well, X is defined to be, just expand this in place, R nor X nor in the sense of 2 S. That's another way of writing it. Then I don't bother mentioning the Y. Why? Because just shove this circuit over here so that it ends up looking like this. the output is here. Okay, and now we have R, S, and we have a dangling X. And the point is I want them to be the same. Okay? So now the question is, there's some, did I do this right? R or, yes. So this is, let me just write this here, question mark. That's what I should say. Okay, so I'm wondering what the hell is going on with this. Because you see, what I'm pointing out is that it's self-referential. It's a kind of circular definition. So we can't take it to be a definition without saying something. And depending on your particular experience, I find often young students, when I teach them, consider that something like this is sensible, just taken for granted, because if you fire up Java or something, it'll accept something that looks more or less like that. Well, yeah, but let's try to figure out what's actually going on here. Okay, so the question is, what I really am trying to do is I'm going to say solve for x. Okay, that's what I want to do. I want to solve. So in general, it looks like this. I'm saying, here is an e, and I'll write x here maybe. It's some complicated, I don't care what the expression is, but it might have some x's in it, such as this one. Okay? And what I want to do is solve that equation. So what I'm looking for, if you think of this as a function, so we can think of this as some kind of function of x, right? That it's a function given by substitution. That is, when I plug in for x, it substitutes it in for e. So what I'm trying to do is solve the equation x equals f of x. It's like an eigenvector for a linear transformation with eigenvalue 1, right? Would be the idea. Okay, so I'm trying to solve for this equation. So the question is, why can I solve for it? Well, the standard answer is, it always has a solution, provided you allow me to say that the undefined thing is solved for it. Okay, so this is what I'm going to do next. Okay, so I need a picture here. So the terminology that we need is, we seek what is called a fixed point. That's what I meant by referring to eigenvectors. A fixed point for f. Okay, which is the substitution function. So you can look at this, the function which, given something, plugs it in for x and e. That's what I mean by this. So we're seeking a fixed point. Okay, so that's the idea. What does it mean to be a fixed point? It means that if you think of it in a sort of demonic way, f is desperately trying to be different from its argument, and you're going to defeat it. Okay, that's one way to think about it. Okay, so the fixed point, the existence of a fixed point, says I've defeated that bastard. Okay, so that's the idea. Now I don't have it on the table, but you might wonder, suppose the equation x equals x plus 1, what happens? Oh, you can solve that in Haskell. Do you know that? You can. All right, I'll explain in a minute how that works, which is what leads up to my issue about variables, so we'll get to that. Okay, I'll erase these diagrams. Okay, so I'll erase these diagrams. So now, okay, so what do I want to do? So here's the way I'm going to do it. I'm going to go back. I have x and I have some stuff. It doesn't matter anymore whether I do it with the VDDs or the NOR gates. It doesn't matter. Okay, I just needed something to get started. But the important thing that I want is to calculate a fixed point. That's the important idea. Okay, so I want fix xe. That's the pretty standard terminology. So the point is, think of that, if you want to use my analogy with functions, it's fix the function that's given x, sends it to e. So whatever you give for x, it plugs it in e sub x. That's a substitution function. It's conventional to write it with a dot like this because of lambda calculus in church. Okay, so that's what we're doing. Okay, so it's a substitution function by definition. That's what that is. Okay, so I add that to my language. Now if I do that, then my RS latch, which I can think of as parameterized by RNS, those are leads that haven't been hooked up yet, okay, can actually be given a definition now, which is a fixed point. And I'm doing a fixed point on x, and now I write R or 1, x or 2s. That's the definition. That ties the knot. Okay, that's the thing. Well, I guess I did want the picture after all. I thought I didn't need it anymore. So we start out in this state of affairs. where there's no question of it being well-defined. And now I need to tie the knot. I need to put that guy in here. That's my x. So what I'm doing is I'm saying the whole thing, when I plug it in here, it stands for the entire thing again. Okay, so that's the idea. So how do we give it, we have to worry about what it means to give it the statics and the dynamics. So the statics, okay, says the following thing. Assuming x is a circuit, E is a circuit, then fix xe is a circuit. That's the statics. I'm done. That's all there is to it. Because it's a circular situation. That is, I'm trying to define a circuit, x, which refers to that circuit. So that's what I say here. And then if so, that's the solution. So this is the, I'll write in quotes, solves the equation x equals E. Okay, where I'll emphasize that x can occur in E by writing it like that. And that's the statics. So that's what we do there. So I can write it down. And then the other thing I can do is give it a dynamics. Okay? And I'll swap boards. So what does the dynamics look like? Everything is the same. I don't mind BDDs or NORs, I don't mind. Okay, so we have fix xe. What does that evaluate to? And then this is going to motivate two very important ideas, which I'll pick up next time. Okay, so how do we evaluate this guy? Well, here's the trick. It's a recursive self-reference. So what do? All you do is you say, plug the thing in itself for x and evaluate that. And if I get a value, then that will be the whole value of v. And I will write exclamation point here. Because this is a use of what is called the Y combinator. That's essentially what I'm doing, aka a fixed point combinator. And this is an idea that was invented by Kleene. Okay, who was my academic grandfather. And he was a student of Church's at the time. You ever look at the, I always bring this up, because I think it's important to bring it up, which is, you ever look at the, what is it called, the math genealogy database? Would you like to know how many descendants Church has, in the subtree? Take the subtree and count. Okay, would you like to know how many the Church has? Does anybody have any idea? Have you ever looked? Would you like to guess how many he has? Last time I checked, it was almost 5,000. You know who competes with that? The Bernoulli brothers and Gauss. Who you just, Oh, Euler, I think, also, again. Okay. But they had a couple hundred years head start almost. So, all right. So he's one of the descendants of Church. Everything I'm doing here is in the school of Church. Okay. So now what we can do here is that what I want you to do now to figure this out is let's do a little calculation. And what I will do is I'll make this false and this true. So the idea of an RS latch, I'm not taking account of the passage of time. I'll get to that in a minute. But the idea of the RS latch is, in that picture, oh, well, the top one is supposed to be R, got erased. You're allowed to either set R to be true or S to be true. You're not allowed to set both of them to be true or both of them to be false. If you set, let's say, the S to be true, like I've done here, it's supposed to converge and latch onto the value being 1, that the output will be set. On the other hand, if you set whatever you do here, if you set this to be true, then the output will be 0. It clears it, okay? So we can just calculate this, okay? So how does this? So that, by definition, is that fix. Write it physically on the board. We can refer, I hope, to what I wrote up there. Yep, good, all right. So how does that evaluate? So we say that this evaluates to something. I'm going to claim it's going to work out to be true if what? Well, if the unrolling, it gets a little tedious. I'm sorry, but I can't, I have to do this once, and I won't make you suffer through it more than once. So I'm unrolling this, okay, and this would be nor S. Right, and this is, I forgot to plug that in, and this is true. So that's the situation we get in, false nor the RSL again, and this being true. Okay, so we do this. And if this evaluates well, it's going to be the same thing. We'll figure it out. And why does that evaluate to something? Well, if this is false, then we're forced to evaluate this guy. So if you don't mind me abbreviating. So this guy is false. If you remember, you have to remember the rules because I think they're no longer on the board. This was the test this first example. So I test this. Oh, it's false. I can't make a decision now. I have to defer a decision to this guy. But this guy tests this first. And it says, oh, well, if this is true, then the whole thing has true. But then this guy, by virtue of testing the second guy, negates it. Okay? So did I get that right? So this, one of them will come out to be false, and then this will come out to be true. Which it does. And then this will be true, and this will be true, and the latch will have latched onto the true value. Okay, so you have to do this calculation. So this is evaluates to true because that's a false. So then this has to evaluate to false because it negates what it sees over here. For this to negate, this because this is true will evaluate to true. Oh, did I do it right or did I do it wrong? I don't know what I did now. If I did it right, you can do it right. Okay, work it out. I hate doing these. I should write them out by advance. But if you just calculate it out, you'll see that it works. I'm going to show you a better way to see that it works in a minute, but I'll get there. Okay, so you can just calculate this out. Now what I want you to notice is the following thing. If you set them both to false, it's undefined. It just oscillates. Because when this one is false, it says, consult this guy. If this guy is also false, it says, consult this guy, which is the thing I'm trying to figure out. So in the jargon, you say the circuit is metastable. I don't know where that word comes from. But anyway, it diverges, doesn't have a well-defined behavior. Okay? So that's the thing you have to notice here. This has no value. It's illegal, so to speak, to set them both to false. So that's the idea. Okay, this brings up two things for me. What have I done here, okay? When I use the fix, when I defined it like this, a notation that you would often use is to say, this is by definition, this is the part where I said young students often aren't bothered by writing something like this. You just write this, and you claim that that's the definition. That's what it means to, when I'm allowed to make a recursive call. Recursive calls are the essence of computation. As soon as I've made the RS latch, it's a bit of a long story, but then I can build up a digital computer from this. Okay, it's a very basic thing. The recursion gives you the passage from the analog to the digital domain. That's the thing, because it latches, it has memory. So what I'm doing is I'm introducing a memory element. I can't say that right now because I haven't introduced a passage of time. So forgive me a little bit that I have to anticipate certain points, but the intuition about it will be that it persists over time. So it's a piece of memory. Okay, so this is called a recursive call. So I want you to notice something, just because it's an axe I like to grind, which is, yes, okay.
Are you missing an L on the RS in the parenthesis?
Am I doing what?
Should it be RSL in the parenthesis?
Oh, yeah, it should be, yeah. Yep, you're right, thank you, yep. Okay, good. All right, so now I'll grind my axe. Take the picture I have up there, or take this equation, take it as defined as a fix. Okay, however you want to do it. I implement recursion. Needless to say, because if you think about this, about how hardware is built up, there are no stacks involved. Whenever people in intro CS worldwide, they teach you about recursion, they go on and on and on about the mysterious stack, which is nowhere in evidence in your program, and as a matter of fact, has fuck all to do with recursion, okay? Nothing. It has nothing to do with recursion. They are not related. What? Yes. And I'm showing you this true because where's the stack? There's no stack. I just unroll the recursion. It's got nothing to do with stacks. Okay? And then that error is propagated in Python, who proudly say that they do this wrong. And they insist on using a stack when it's not called for to implement recursion. Okay? So the reason I want to be finicky is because mistakes compound. Okay? And it's better if we try not to make them to begin with. So my first point is there's no mysterious stack involved. Forget all that. Okay, that's nonsense. It's just a simple unrolling of the recursion. That's what the fixed point thing is all about. Okay, good. Now I want to say the following thing. Going back to Robin Milner's question. How do I say that what I've got is well-defined? Okay, that's the thing I want to get to. Preliminarily to do this, I made a remark here. This has no value. So you might think, oh, this is a weird thing. If I'm solving an equation, I can solve it by like saying the undefined thing is a solution. That's exactly what you do in Haskell. Okay? So that's like a very strange thing because look, if you look at just fix, the most blatant one is fix XX. Call yourself. Okay? This evaluates to V if, well, unroll it. Plug in fix XX for X in X. It's true if it is. So in execution terms, it's just diverging. Okay? So my point is we now have a weird situation because we use substitution to define this. But this may not stand for anything. So in ordinary math, like especially elementary school math, they kind of dance around this question. What are you supposed to do with 1 over 0? Am I allowed to plug it into a polynomial or what? Okay? It's a little fuzzy. Okay? It's a little fuzzy because it messes up a lot of things to have undefinedness because partial functions are a little hard to deal with. It's easier to pretend things are total. That's kind of the idea, okay, approximately. And this is where some things happen. This is the manifestation of it. This is an analogous thing to like 1 over 0 or something in the context of programming where it's the fix, the possibility of calling yourself infinitely leads to an undefined behavior. So what I have done to you so far, I've pulled a trick on you, okay? What I've done is by putting this in, I'm going to be able to revisit and prove the structural properties the way I stated them. In particular, transitivity or substitution. But the expressions E may not stand for anything because it might be a fix. So in particular, the expression RSLFF doesn't stand for anything. It's 0. Okay, it doesn't stand for anything. Okay, so there's something weird about this because what I'm doing here is the setup. So we can check. So now you have to check the coherence. And now we're going to have problems. Okay, so first of all, the structural properties hold. And the structural properties, in this case, state that we may substitute, and I'll use some terminology which will help me in the next lecture. I'll call it computations for variables. Things that potentially stand for something but maybe don't. Okay? That's the idea that, oh, after all, this complicated thing, I suddenly realized it actually diverges. Okay? But we're nevertheless allowed to plug it in. In other words, variables range over computations. It's the range of variables that is important because the whole idea of the consequence relation and the structural properties is to say something to you about what variables mean. And if you want them to be more like math, you want them to stand for values, not for computations. I'll come back to that for the exact reason that I mentioned a moment ago. And I'll just write here versus values, and I will pick that up a little bit later, okay, but not this moment, okay? If you review them, because it says I can always form, if you look at the structural property, which is no longer on the board for me to refer to, I allow myself to form that whatever E1 is, and it might even be RSL false false, and it might be undefined. That should make you a little uncomfortable, okay? But that's the way it is, okay? So that's the definition. Okay, good. So that's the structural properties. They've told you something important. They've told you what variables range over. They range over computations. You must pay attention to these things because in a computational setting where we embrace partiality. Why do we embrace partiality? There are people who wish to get rid of partiality so nothing is ever undefined. Well, it's all very nice on paper, but there's a little thing called the Blum size theorem, which you ought to know about. which basically says if you insist that every program you can write is totally defined, think of it as using only for loops with fixed bounds for I equals 1 to 10. Okay, that's all you're allowed to do. You're not allowed to do while loops. You're going to think about it intuitively. A program is going to be a fat pain in the ass. Okay? Why? Because you're encoding the termination proof into the way you write the program. And Blum's size theorem says you can pump up the size of a program as much as you want by making the termination proof be so god-awful that that to encode it as a piece of code would make a gigantically long program. That's a theorem. Things like the Collatz conjecture, you might have heard of that. Very elementary function you can write down recursive in ML. Nobody knows if it terminates. That's on all inputs. Nobody knows. As far as I know, it's an open problem, and serious people have seriously looked at it, so it's pretty unknown. If you don't know about it, look it up on Wikipedia. Okay? All right. Okay. So that's what we're saying about these variables. But how do we know that the language makes sense? Okay. So an obvious fact, given everything I've said, E's need not have V's. So the previous theorem isn't going to hold. Okay? The previous theorem was, if E is well-formed, if it's a circuit, then it has a value. Not true here. That's what I just said several different ways. Okay? So that's not the case. So what is the right thing to say? Well, the situation I want to worry about, what did I do for, I'm suddenly blanking on what I used for an example. Otherwise, I'm going to have to think of an example off the top of my head. What did I do here? I came up with a good example. Give me a moment. And I don't know what it is. I'll get to that in a second. Oh, okay. Oh, forgive me here. All right. Okay. All right, so here's what I'm going to do. All right, so the question is, what do we say instead? So the idea is, that's important, okay? So the way I'm going to do this, there's another motivation which I can't get to until next lecture. So let me skip that, okay? So I'll get to that in a minute. But what I want to say is, the issue is this. That there are, in general, yeah, okay, I'll say it like this. In general, there are many, I don't know what to say, many sorts of undefinedness. And I don't want to lump them all into one big bucket, okay? I want to deal with the divergence, okay? So I want to say something meaningful that accounts for the possibility of divergence. That is, it meaningfully says that the language hangs together and is coherent, but it allows the possibility that things are divergent. So the way we introduce this, and I want to be careful, I want to distinguish divergence. That's what I want to do here. I want to distinguish divergence from complete nonsense. And in this lecture, I can't yet give an example of nonsense, but what it would be something like, I don't know what, if I had addition on numbers true plus 17, okay, it's complete nonsense. It has no value. That would be what would happen shortly. Okay, I'm foreshadowing a little bit. Okay, I want to distinguish that from something which is, I claim, is perfectly sensible, the fixed point, but it can diverge. And the reason I want to allow divergence is because I don't want to run into the Blum size theorem. Everything has a reason. Okay, so this is again what I'm saying. This is the inside baseball. Okay. All right, so this is what I want to do. So the way we do it is we introduce the notion of passage of time. Introduce an idea of time. This will lead to complexity analysis of programs, and I'll get to that in a lecture or two. I'm going to talk about that. So it's important to do the passage of time. In particular, it will allow us to express the coherence. That's one reason why we're doing this. That's the primary reason. But it will allow us to express, in the circuit terms, propagation delay. We'll see how propagation delay works as soon as I do what I'm going to do next. Okay? So what is it that I'm going to do? That I'm kind of hovering around here trying to figure out what I'm going to do. Okay, I'll tell you what I'm going to do. So what I'm going to do is, because I no longer have this nice termination property, I have to figure out some way to say something meaningful that lets me distinguish various varieties of errors and lets me express things like propagation delay and so on. So how do we do this? What is called SOS, and it doesn't mean help, it means structural operational semantics. And it's a nice idea for the following reasons, which I'll explain. So it's a different way of specifying the dynamics. And the way you do it is you define a transition system, state transition. It's a state transition system in which the states are closed expressions, because everything's really elementary in this lecture. Okay, so the states are these, so it's state transition, but the states are the expressions. And then we have a notion of a final state, which is a value. Final state, you can put it like that. Everything is an initial state, so I don't bother specifying initial states. Any expression is an initial state, so I don't need to specifically say them. In some other setting, I might need to do that. Okay, so we have this thing. Okay? And guess what? These are inductively defined. In a particular case, I say true is a value, false is a value. That's all. That's the inductive definition of values. Okay, there's nothing else. Put that over the side. Then how do I evaluate? Now let's look how we actually do this as a state transition system. So let me do it with the NORs. It doesn't really matter, but let me do it. Okay? So I'll say the way NOR 1 works is it looks at the first argument first. So if you can make a transition on the first argument, then by all means do so, because I am very interested in what your value is. Okay? So I do that. Yep. So I do E1 transition to E1 prime, then this. So this is a rule that we will have. Okay? And then we'll have another rule. And if I have true NOR E2, then that evaluates the false with no premises. And this is all for NOR 1. You can do NOR 2. Okay? I may have forgotten to mention. Okay, I'll get back to the NOR 1, NOR 2 distinction in a minute, because I think I forgot to. No, I did write it up there. Yeah, okay, good. I was making the distinction. Okay. And now what I want to say is, oh, yes. So now, if E2 can make a transition, under the condition that we already know that this is false, that this is true, in that scenario, that I already know this, then I'm allowed to work on E2. So the important thing about how the latch works, you should play around with it for yourself. The latch only works because I'm doing this, okay? Otherwise, it doesn't make any sense, okay? So I have to do this work. So if I already know that the answer couldn't be determined cheaply, so I have to do it the hard way. And then how do I do it the hard way? Well, if you give me true or true, you'll become true. This will become a false, if I'm not mistaken. I think that's right. Yeah, is that right? Yeah, I think that's right. And then if I have true, I'm still in the situation where I know the first thing is true, but the second thing turns out to be false. Oh, well, anyway, then this will turn out to be true, because I'm negating the second guy. Okay? So I'm doing the opposite here. Okay, that's the negation part. And then you can do plus the NOR 2. Okay, good. All right, now so we say this is also an inductive definition. And now the thing we want to refer to here is the concept of safety for partial languages. That is, languages with divergence. Okay, and I'm going to allude to this here. So what I want to say is the following thing. So what do we say instead? Well, let's kind of thrash around a little bit here. I'm going to introduce time. I'm making room for myself. Okay, so what do we say instead? Well, we want to say something like, the statics makes an accurate prediction of the behavior in the dynamics. So we want to say that if the statics says this is a well-formed circuit and it's closed, then I want to say something. I'm not able to say there exists a V such E evaluates to V, because that might not be the case. So what can I do? What can I do? What can I do? Well, once I introduce the passage of time, and then we'll see how it handles the problem that I foreshadowed. Once I introduce the passage of time, I can do the following thing. I can say, well, if E is a circuit, and it actually makes a transition, then it doesn't run off in the weeds. And E prime is still a circuit. You might think, isn't that obvious? Well, in a certain sense it is all obvious, but I'm trying to show the anatomy of the situation, okay? So it's not the obviousness that I'm after, it's the anatomy, okay? So you can say it like this. It says, well, if I could take a step, then the result will again be a circuit. And then I will know the following thing, which says that if E is a circuit, then either, and we say this either, E is a value, in which case I'm done, or E can take a step. And what am I doing here? Why am I doing this? Well, one thing is I'm introducing the passage of time. So what I maybe forgot to emphasize here is, let me put this here as an exercise. Okay. One direction of this is easy, the other direction is difficult. I don't want to spend time on it. I want to prove that E evaluates to V if and only if E transitions to V in multiple steps. The definition of this is V multi-steps transition to itself, and if it takes one step to E prime, which then multi-steps to V, then E multi-steps to V. And that is called head expansion. So I close it under head expansion. Okay, then you can prove this. This direction is easy. This direction will require a moment's thought. Okay, so I'll leave it at that. Why only a moment's thought? If you have a mastery of inductive definitions, which you ought to do, then you'll realize instantly what it is I need to prove, and then it's obvious. Okay, you'll see what's happening. If you're a little fuzzy in inductive definitions, you might thrash around and do some ugly thing. But I set this up for you so that it will reinforce that point. That's why I do that. Okay. So now we're back to this guy here. So what it's allowing me to say is, so one thing in particular is, there are no stuck states. This will imply there is no situation in which E is a circuit, E is not a value, and yet E cannot make a transition. That will not happen. That's the consequence. I'm running low on time according to Marco. Good. Okay? So this is what it tells us. There is no situation in which you're a well-formed circuit, you cannot take a step and you're not either true or false. Of course, true or false don't take a step, we're done. Okay? So that cannot happen. That's really important because that's telling us there are no illegal instruction core dumped. Okay? I never get into a situation where the goddamn thing doesn't know what to do. It's like frozen in its tracks. It says, oh, I've got a valid circuit and it's not done and yet I can't do anything. That's what is being ruled out here. That's why this covers the other form of errors. Okay? It's telling you that certain erroneous situations cannot arise. No ill-defined situations. Yet, I allow divergence. That's the important thing. Okay? And if I just have a full evaluation relation, there's no way for me to say, given only the down arrow extended with fixed in the way I described, I don't know what to say. Like, there's no way to say it can still take a step because there is no step to take. All I know is E is a circuit and it doesn't have a value. Well, what does that mean? Okay? So here I'm able to say that it must be looping. That's the only possibility. It can be looping. It cannot get in a situation where it's stuck. Whereas you see, E doesn't evaluate to something, that is, there's no value for it. Could mean this diverges, or could mean in a richer setting, it's screwed up in some other way and I can't distinguish them. Here I can distinguish them, that's the point of it. Okay? So this guy is proved by induction on the statics. Oh, excuse me, that's wrong. It's proved by induction on the dynamics. And it's such a simple language it won't matter, but trust me, that's the induction thing you want to do. Here you don't have any choice. You have a mapping out property because that's inductively defined. You're trying to prove if then, that the only game in town. Use the universal property. Here, you work on the definition of the transition. You can go, and notice how these form a pas de deux. Okay? Because if you're a circuit and you take a step, okay, then you're well-formed. If you're well-formed, then either you're done or you can take another step, in which case the step you took to was well-formed, and they keep going back and forth and back and forth and back and forth. That's how this works. That's the heart of the matter. That's where this comes from, okay? And this is called preservation. This is called progress. And together, they're called safety or coherence. So the lesson is, a language is well-defined if you can prove such a coherence theorem for it. That's the baseline requirement. If you don't have that, something is not right. Okay? You haven't said, there's something you haven't said properly, and it has to be worried about. Okay, so that's my brief answer in a very limited setting, to an illustrative answer to Milner's question. Oh yeah, so it's an exercise to finish out. Yeah, what I want you to do as another exercise, very good for you. If you look at RSL now of what did we do before, false, true maybe? I want you to see the number of steps it takes until it gets to true. That will be the propagation delay. You will be able to see it because if I remember correct, it actually takes 2 or maybe it takes 3 steps. I've forgotten. Okay, I wrote it down in my notes, but I'll just put star here to not worry about it. You'll watch the thing propagate and watch how the feedback works and how it makes up its mind, okay, by doing this. Then when we extend it with an element of time, it'll be more interesting, but this is what we can do there. Do that. That's really useful for you if you haven't done this before, so you can see how the tools work and you can see how that goes together. Okay, good. So that's what I have to say for today. I have to coordinate with Jan. He may want me to do recursive types next time. Not quite sure, in which case I'll go in one direction. Otherwise, I'm going to push on this semantics of variables direction, which I like a lot, which, believe it or not, is going to lead into parallelism. And I'm going to tell you about parallelism. So that's, I'm not sure what the fork is. I have to consult with my colleagues. So, okay, so thank you very much for today's lecture. So.